Thank you all for coming. Thanks, Marcus, for the invitation to return to Bonn. It's always with enormous delight that I come back to see you and to speak to you. I think you guys have an extremely active and sophisticated and suggestive community here. I come back home full of ideas after interacting with all of you here. So this is part of a larger project on the notion of identity and how it functions and a number of issues that it raises. And the motivation for today's talk is a claim that has been made in different contexts since the 20th century about some limitations of the application of the notion of identity. That in some contexts, objects do not have identity conditions. There are the kinds of things for which identity applies. And I find myself in the very odd situation of trying to defend the establishment. Right? Usually my views tend to be the sort of the minority, right? And in this case, I think it won't be, right? So what I'll be arguing here is an attempt to answer the question as to whether quantification does require identity of the objects that are quantified over, right? And whether it's even intelligible to talk about quantification over such things for which identity doesn't apply, right? What I'm going to be doing is I'm going to look at a number of arguments to try to argue that identity is fundamental in the context of quantification. Don't be too hung up on the notion of fundamentality, right? Just sort of it's required, it's basic, and I'll argue that classical quantification, that is quantification in classical logic and classical set theories, do require identity. Now, in particular, I'm going to look at three arguments, right? One, it's an argument from the domain of quantification. Second, an argument from the range of quantifiers. And third, an argument from the collapse of the existential and universal quantifiers. And then, once these things are set up, I'm going to suggest that even in non-classical contexts, right, when dealing with logics and set theories for each that include objects for which you do not quantify, identity even there is required. Right? Objects for which identity is not defined. Right? Even there, despite the overt motivations for these frameworks, they actually require identity nonetheless. Okay, now first there are Quine roots here for what I'll be talking about. In fact, when Quine wrote a review of Peter Gates' reference and generality, he does talk about a doctrine according to which identity is a relative notion, right? In fact, that's what Geach is pushing, right? Identity is always relative. There's no such a thing as absolute identity. So x equals y is meaningless on this view except relatively to a parameter. That is, x and y are the same f. That's Geach's point, and Quine complains, right, in his review. He says, this doctrine is antithetical to the very notion of quantification, the mainspring of modern logic. Quantification depends on there being values of variables, same or different, absolutely. Grant quantification, and there remains no choice about identity, not for variables. For a language with quantification in it, there is but one legitimate version of x equals y. Right? I think Quine is right on this. But as is typical of Quine, there is not a single argument here. Right? He doesn't bother. Right? He just assert those things as though they are obviously true and don't require much further considerations. What I'm going to try to do is to say why we do need arguments, and luckily we do have a number of them, and that's what I'm going to be doing. But since I start this business about talking about relative identity, let's just get out of the way why there is not such a thing as a relative identity. So, because to make sense of relative identity, right, x and y are the same f, rather than just x equals y, identity of the same f is presupposed. on pain of unwanted regress. That is, even the notion of a relativized identity ultimately requires an unrelativized absolute notion of identity, the same f, right? Because in this expression, the same f, either identity is relativized or it's not, right? If in the same f identity is not relativized, then relative identity ultimately assumes some unrelativized absolute identity, right? So there you go, you need some identity there. If in the same f identity is itself relativized, then relative to each property is identity supposedly restricted, right? Well, let's suppose that G is such a property, right? In that case, then we have f is the same G, which in turn will invoke identity. If that identity is also relativized, you know, we're off into a regress. Otherwise, an absolute notion of identity is required. So the thought here, and I bring this up just as an illustration as to how basic identity is and how hard it is just to say, look, we don't really need identity, right? It's just some restricted identity, something like that would do the trick. Now, maybe you can say, no, but we can define a relativized identity, right? When you say x equals y are the same f, we can express that in terms of predication as f's and y's. Well, but this just say that y's and x are f's. It doesn't say that they're the same f, right? Perhaps you can say this in this way, right? X is f, y is f, and for any other z, it's one or the other, right? But that doesn't quite do the trick, right? It just expresses that there are at most two f's, which is different from x and y are the same f, right? Second, of course, even in that case, an absolute notion of identity is being used on the consequent. That doesn't work. Well, maybe you can go second order, right, and say x is f, y is f, right? And then you talk about the x's and the y's and say, well, and those things there are the same. Well, maybe that gets a little closer to x and y are the same f. But once again, you have the same trouble. Here you are now using identity over those second order variables. So the unrelativized one on pain of a regress. Now, the easiest way would be to say this, right? X is f, y is f, and they are the same, right? That would say, right, as you want, x and y are the same f, right? But clearly, you're using unrelativized identity there. So the idea is even the thought of trying to express what relativized identity is ends up presupposing an unrelativized notion of identity. Okay. But maybe what's the issue here is not about identity absoluteness, right? The issue is whether the content of what needs to be expressed can be properly expressed without identity, right? And in the end, I think it's just unclear that there is such a thing as a relativized identity, a special kind of identity, right? There is identity, and of course it can be used to express identity claims. As a matter of expressive choice, it can be restricted, right? You can always restrict to some predicate, right? We can always do that. But it's not that it's a special kind of identity, right? Any more than you can say that a soccer player is a restricted kind of human, right? You say, look, there are humans, and some of them are soccer players, right? We're just restricting a notion that applies beyond that. So there is identity, and it can be used restricted to certain properties, right? But that, it's the same notion. It's just identity restricted in a particular context. So the conclusion here is x and y are the same f. That expression, the same f, ultimately does invoke identity and not a sort of relativized identity at all. So Quine was, I think, right in complaining as he was. Now, what are the arguments then to support the conclusion that the very notion of identity, the quantification requires identity, right? So here's the first argument, right? The argument is going to come in different versions, right? We're going to first start in a set theoretic context, and then we're going to extend contexts in which set theory is not assumed, right? So here's the argument, the first one, the argument from the domain. So quantification requires a domain of things over which one quantifies, right? That seems right. Typically, that domain is a set. And certainly in the set theoretic context, that's what we do. In classical set theories, of course, extensionality holds. So we have the two sets are the same as long as they have the same members, right? As a result, of course, identity is assumed in order to characterize the domain of quantification as a set. In fact, what extensionality forces us to do is to say, unless the things that are being collected as a set have identity conditions, we cannot distinguish whether two sets are the same or not, because the identities of the sets are going to be mapped back on the identity of its members, right? And extensionality forces them, right? The identity of a set that is formed from the objects can only be specified given the identity of the objects of the set. So by extensionality, two sets are the same, just in case they have the same members. And since quantification is then implemented over a set, the domain of quantification, identity is assumed, right? That's a simple argument. You say, look, if you're in a set theory that has extensionality, you're already in a framework where your quantification, because it requires a domain of things, would only be applicable to objects that have the identity conditions, right? So we don't have quantification here without identity. Now, suppose, however, you're not in a set theoretic context. You say, look, that's too cheap. Of course, extensionality will force you to do that, but well, let's leave it that behind, right? So I think it's a little more complicated, but the argument can be made also in a context that does not, where your domains are not sets, right? So we start in the same way. Quantification requires a domain of things over which one quantifies. This domain need not, in fact, should not be a set, right? What we need is to quantify over things, not the set of those things, right? So in a way, having a set is just a very convenient but ultimately dispensable device to specify the range of quantification. What makes it very nice to have a set is because then you have very clear specification of the things that are in it and the things that are not. So you know exactly the boundaries of your quantifiers, right? So what we need to do is to mimic that without sets, right? Now, the thought here will be, well, but what we want is just to make sure that we are quantifying over those things that we are quantifying, right? So instead of having a set of f's, right, the things that we are in the domain, all we need is just the f's, right? That's all it's required. However, and this is the key complicated point of this argument, each f needs to be distinct from one another, and thus identity has to be applicable to them. Now that's the little part that will need argument. You said, well, why is it that if you have just the f's that you're quantifying, whether each one of them needs to be distinct from one another? So now here, there will be a multiple step argument to support that conclusion. So first premise, quantification requires counting, right? Only certain things can be quantified over. That is to be in the range of the quantification, although they are not taken to be a set, right? Namely those things that can be counted, right? In particular, it's not possible to use a quantifying over mass terms, right? So for example, if you say things like each water is liquid, or every water is transparent, right? Of course, these are ungrammatical, and there is a reason why they're ungrammatical, right? Because the count noun is required here by each quantifier. Now, I think this results from the fact that quantification will range over things that can be counted, right? Quantifiers, after all, deal with quantities of some sort. Some, all, most, right? So that first premise here, just make that link, right? Quantification requires counting. Second, counting requires distinguishability, right? Basically to avoid double counting, because you may just be counting the same thing again and again. So just to flesh this out, suppose that things A and B can be counted. In this case, minimally there will be a one-one mapping from each of these things, A and B, to, say, the first two natural numbers, 0 and 1, right? That just comes from the assumption that they can be counted. And as a result, of course, you can distinguish these things via this mapping, right? And you don't need even to talk about Leibniz principle of identity, right? Here, you're just sort of mapping them into numbers 0 and 1. So the assumption that certain things can be counted would require their distinguishability, right, to avoid double counting. Third premise, distinguishability requires identity. Now, there's an easy way to see that if you help yourself to Leibniz principle of indiscernibility of the identicals, right? Because if you have that, right, the principle tells us two things are the same as long as they have the same properties, right? If they are distinguishable, then they are not the same by modus tollens. For there's some property that distinguishes them, right? So in that sense, you get easily the distinguishability will require their identity. Now, of course, identity of indiscernibles is actually problematic in the context of those people who think that there are things for each identity. Doesn't apply. Because they're going to say, look, that principle you cannot just pick and apply to quantum particles. I'm going to return to some of these arguments later on. So it would be nice if you can make that premise without assuming identity of indiscernibles. So here's a slightly more complicated way of getting to the same conclusion, right? I'm calling the hard way. It's just a little, not a lot more. But it doesn't assume Leibniz principles of identity, right? So again, we start with these two things that are distinguishable. Then there is something that distinguishes them, or that can distinguish them. Can these things still be the same, be identical to one another, those things that are distinguishable? If they are the same, then they will be distinct, identical things. A contradiction, okay, that wouldn't be good. If they are not the same, then they're just distinct things, but identity is applicable to them, right? Since they're not the same thing. Either way, identity is applicable, right? Whether they are consistent things or not. And you do get the same conclusion that distinguishability will require their identity, right? Okay, and as I said, one of the whole motivation to question whether quantification requires identity comes, from, well, you trace all the way back to Weil and Schrödinger interpretations of quantum mechanics that says, look, it doesn't make sense to apply identity to quantum particles. They are not the kind of things for which identity emerges. We're going to see one of these arguments in a moment, right? And the contemporary scene, the most thorough defense of that view is in a lovely book by Stephen French and Décio Krause on identity in physics, where they develop a framework to think, quasi-set theory, to think about quantification over things for each identity doesn't apply, right? And what I'm trying to do is to say whether we really can make good sense of what the quantification how quantification functions in the context of this framework. Okay, I'll return to it in a moment, right? My point here so far, it looks like, if you have distinguishability, which they have, it looks like identity of the objects can always be raised, right? So in the distinguishability would ultimately end up requiring the identity, right? The identity conditions of the things, right? That you can say they are the same or not. Okay, so we have, if we put this together, we have here the first known set theoretic version of the argument from the domain, right? First premise, quantification requires a domain, the things that are quantified over, which is not taken here to be a set. Given a domain, quantification requires counting, right? In the sense that quantified range over things that can be counted. Counting requires distinguishability, so you don't have double counting. Distinguishability requires identity, right? In the sense that it can always be applicable to these distinguishable objects. Hence, quantification requires identity, right? And this is an argument entirely outside the context of set theory, right? So you don't rely on extensionality. It doesn't rely even in the principle of identity of indiscernibles. So it's an argument, that has some, it's meant to have some generality. Okay, now, if you don't have sets, right, to give specify the range of your quantifiers, you need two conditions to be satisfied about this range, right? One you can think about as sort of a completeness condition, right? Quantifiers range over each object of the domain so that all objects in the domain are quantified over, right? You make sure that that happens. And of course, you need some adequacy condition for these domains as well. That is, no object distinct from those in the domain is in the range of quantifiers. We never need to bother with doing that if you're in a set theoretic context, because you get the completeness and adequacy just by having your sets, right? And say, oh, this is the range, right? But as we saw, if you are in that context, you have the identity conditions sort of ensuring that the range is properly specified. Now, the completeness condition will guarantee that all objects in the domain are included in the range of quantification, so nothing is left out. And the adequacy condition guarantees that no object distinct from those in the domain is included in the quantifier's range. So you don't put in things that are not part of that range. But the point is, both conditions require identity of the objects of the domain. Why? So think about completeness, right? Quantification cannot be implemented over a thing to which identity doesn't apply, right? As we saw, quantifying relation over things that can be counted, which requires identity. So each distinct object will be quantified over, right? So you need to have that, otherwise you don't that notion of distinctness, so not identical. So you can make sure that, look, all of them are here. And the adequacy, also no object distinct from those in the domain, will be in the range of the quantifiers, right? So nothing, you're not quantifying over things outside that context. Now, someone may complain, right? You may say, but wait a minute, that adequacy condition here, the way you formulate it's tendentious, right? You could express it without identity, right? So let's call adequacy star, right? And you say, look, no object that it's not in the domain of quantification is in the range of the quantifiers. Or alternatively, only those objects in the domain are in the range of the quantifiers. So you forces just to make sure your quantification is within that context. So on the first is, on the surface, it looks as though I now specify the adequacy condition without talking about identity, right? Or without requiring the identity of the things in the range of quantification. Despite that, I think, even adequacy star ultimately presupposes identity. Why? In full generality, for an object not to be in the domain of quantification, it will need to be different from those that are in the domain. Otherwise, it would just be one of the objects in the domain, right? And that's what forces you to bring in the notion of identity. Say, look, my range is such that none of these things that you're not quantifying over actually, it's part of that. And for that, you need the notion of identity. So even in that case, for that kind of quantification, identity is required. So we have a second version of this non-set theoretic formulation of the argument from the domain. It goes like this. Same first premise. Quantification requires a domain, the things that are quantified over, although not a set of them, and arrange the scope of the quantifiers, right? So you quantify over those things, not over these other things, right? The range of the quantifiers need to be complete and adequate with respect to the domain of quantification. So you make sure you're quantifying over all and only the things in that range. Completeness, as we saw, requires identity. Adequacy also requires identity for the reasons we just seen. Therefore, quantification requires identity. Right? So whether you're in a set theoretic context or not, it looks like the idea of a domain of quantification is such that it forces the identity of the objects in order for you then to be able to quantify over them. Okay, so that's the first argument. Now let's second argument, right? The argument from the range of quantifiers. And that's sort of a familiar argument if you consider. Now we're going to move to sort of a kind of model theoretic semantics, right, for our logics, right? So when you think about the way in which quantification is often introduced in books about, say, here in first order logic, you have Mendelssohn, for example. We're all familiar with a condition such as this, right? A sequence S of objects of the domain satisfy a formula for every xi fx, as long as every sequence that differs from S in at most its ith component satisfies F, right? The familiar kind of definition of satisfaction of objects in terms of sequence of them, right? The point is here, that kind of model theoretic approach assumes that every sequence that differs in what, so every sequence whose term is an object that differs from the others satisfy the component. Of course, sequences are functions from natural numbers to objects of the domain. In order for two sequences to differ in their ith component, these components need to correspond to different objects in the domain. So the objects in the domain have to be things for each identity applies. Right? So that's another way of seeing in the very formulation of your quantification, you have now a method theoretic framework that forces the identity onto the quantification. So that's the argument, the range, the argument from the range of quantifiers, right? Now, as I said, one of the motivations to think about why identity may not be applicable across the board comes from known individuals in quantum mechanics, right? So, and I'm going to consider here sort of non-relativistic quantum mechanics for a moment, right? So the view that French and Krauss sort of discuss in their book. On this view, the most natural way of sort of making sense of certain interpretations of non-relativistic quantum mechanics is by understanding quantum particles as known individuals, right? So things like electrons, photons. So they will be known individuals in the sense that identity does not apply to them, right? Now, notice, this is not to say that they are different from themselves, right? I don't know how can anything be different from itself, right? The thought is different. The point here is that identity fails to apply, right? So when you have, given the formalism of the theory, the idea that you can say, look, this electron is the same as this one, or it's different from that one, doesn't make sense, right? So that's the thought here. And you may say, look, but that's a very bizarre thing to say. Why would anyone think that that's plausible to take that route? And as it turns out, it comes very naturally when you think about the quantum statistics, right? So let's just look for a minute in a very simple case when you have a sort of a classical statistics, right? Suppose you have two boxes, right, and so two objects, A and B, and two boxes. So there will be, of course, four possible distributions, right? You can have the two objects in one box, none in the other. The first box empty, the two boxes, both of them in the second. They can be distributed, one object in each box, or the reverse. These are all the four possible combinations. And if you assume that each of these combinations has the same probability, right, the conclusion will be the probability of each possible combination is 1/4. Right? There are four possibilities. If they're equiprobable, that's what you get. Now, things don't quite work that way in the case of the quantum statistics, right? Because there we are in the following situation. You're considering now, say, let's suppose an electron, right? Now, an electron is not a little ball, right, spinning around. But think of it just for the sake of argument for a second, right? And the thought is, if you have a quantum system that is in a certain state with that electron, sort of spinning around, if you were to replace that electron by any other electron, you would not change the quantum system the system is in, right? And that principle, it's a crucial feature. So there's a sense in which it doesn't matter which electron you are considering. You can swap that for any other electron, and the quantum system will be the same, right? In other words, there is no way you can mark the electron. So go there, make a little note, and say, okay, this is Ike, and this is Mike, and I'm going to swap them, right? As W.V.O said in his lovely style, he said, look, given Ike and Mike, there is no alibi to an electron, right? You can never tell which one is that, right? The idea is, given the way that the theory is formulated, right, nothing about the quantum state would allow you to individuate these guys, right? So the thought is, okay, so in a way that you would in a classical object, I can always mark things and say, yes, this is one object, this is another one, right? And this is not just an epistemic point, right? On that interpretation, something about the nature of these objects that prevent them from having that kind of labelings. All right, so here's how the quantum statistics is different, right? So again, suppose you have two indistinguishable particles, say two electrons, right? Swapping around. If you swap them around, you don't change the quantum state they are in, right? So in that case, suppose you have the two quantum particles in two boxes, or two states of the system. So you have the following possible states. You may say, I have two electrons in that state, none in the other. Maybe this, vice versa, two electrons in the other state, none of the other. And then I have two other options. One in one in the other, or one in one in the other. I cannot distinguish, right? The situations 3 and 4 are entirely indistinguishable, right? Exactly because swapping around these guys doesn't change the state they are in, right? And that, of course, because of 3 and 4 actually are not different states, now we have only 3 possibilities in effect, right? So, and if each state is equiprobable, you have the probabilities here are going to be of 1/3 rather than 1/4, right? And what's nice here is the following. This drops out very naturally from the way in which it gives you the right quantum statistics just by thinking of these objects in these ways, right, as being non-individuals, right? And that's why W.V.O, Schrödinger, and others suggest, look, this is the way to interpret quantum mechanics. Of course, you can interpret it in some other way, but then you have to do a song and dance to say how come that the probabilities are 1/3. If you're able to distinguish these things, why is it that you get these 1/3 probabilities, which are in fact the ones that you get empirical support for, right? So there's something to be said for looking at the issue from that point of view. Okay. Now here's my question. I'll grant all of that. What does it mean now to quantify over these known individuals, right? Because there are things for each identity. Doesn't apply, because if you were to apply, you're going to mess up the statistics here. Right? Well, you violate quantum mechanics on these interpretations. So to try to make sense of that, what French and Krauss does is to introduce a theory that Krauss had earlier formulated, a quasi-set theory. Right? So the idea is, this is a set theory that, as opposed to the classical set theories, identity doesn't apply to all objects. So it's a two-sorted theory. Right? There are some macro objects for each identity applies, and you have micro objects, like electrons, for each identity doesn't. Then instead of talking about identity for these micro objects, all you have is an indistinguishability relation, right? Which is, of course, an equivalence relation, right? So even though you cannot say that an electron is the same as the other, you can say, well, electrons are indistinguishable from one another, right? And that's the sort of the insight here, right? And of course, they've they offer an axiomatic system for quasi-set theory. I'm just going to give the first 3 principles for today. The ones that actually say that that relation of indistinguishability is indeed an equivalence relation, right? It's reflexive, it's symmetric, and it's transitive, right? One of the complaints I make is right here. You're ready, despite the goals of avoiding the presupposition of identity, you still have, right? Because if you consider, for example, here, right, these indistinguishable, say electrons, if you're considering them, right? Whatever is playing the role of this guy here has to be playing the same semantic role here, right? Otherwise, instead of expressing a symmetric relation, you would get, if it's some other functional role here, you would express some other relation. So even the formulation of the principles presuppose the identity. In that case, an identity about the semantic role of the expressions in the language. And that shows how hard it is to get rid of this damn thing, right? Okay. And I think once you're there, there are a lot of inferential troubles that would emerge by the way that the theory is set up. And that brings us to the third argument, right? The argument from the collapse of the existential and the universal quantifiers. Okay, so suppose we are somehow quantifying over those known individuals, right, over those electrons, right? Suppose one of them is F, right? So A is F. And then you infer, okay, then something is F, right? You can infer that. So far, so good, right? So we have this inference, a familiar inference. If A is F, something is F. But then you go with the following little arguments, right? Since no individuals are indistinguishable and identity doesn't apply to them, if a known individual A is F, then all known individuals indistinguishable from them are also F, right? Because nothing will distinguish them. If one is, all of them are. But in this case, it means that we just satisfy that somewhat odd inference. If A is F, then everything is F, right? But that, of course, we don't want that, right? Because that's, of course, it's an inference that is typical of the existential quantifier, not the universal quantifier, right? But the indistinguishability of the objects would allow us to do just that. Now, we have problems on the other side as well. So suppose that everything is F holds for these known individuals. Right? Then, of course, in particular, if it holds for all of them, it holds for A in particular. So A is F. So we have the inference, the familiar one, from everything is F to A is F. Consider now that that something is F holds, again, for some known individuals. Since known individuals are indistinguishable and an identity does not apply to them, if something is F holds for some known individual, then all known individuals indistinguishable from them are also F. In other words, if everything is F, A is also F. As a result, then, we have an inference that it's, of course, typical of the universal quantifier, right? Something is F, therefore A is F, following. But you don't want, presumably, you don't want that to be the case, right? In other words, right, we have the following inferences holding for known individuals. If A is F, everything is F. If something is F, A is F. And what we have in effect here is a collapse of the existential and the universal quantifiers, right? Because you have inferences that are typical. The first one is a typical inference for the existential quantifier being satisfied by the universal one. The second one is an inference typical of the universal quantifier being satisfied by the existential one. So you collapse them. You're no longer in a position of sort of distinguishing these quantifiers. Note that I want to say that this collapse only emerged due to the fact that the identity was not assumed to hold among known individuals. Why? Because the validity of the inferences above will be blocked in the presence of identity, as it is in classical logic, right? Fa doesn't guarantee that everything is F, since an object different from A may not be F. right? That's in fact how you say, look, that doesn't, from A is F doesn't hold that everything's F, because you have this other object here that is not F, right? But this other object is different from A, so you have identity there. Similarly, something is F doesn't guarantee that A is F, since A may be different from the object that guarantees that something is F, and A may not be F. Again, you say, look, if something is F, that doesn't mean that A is F, right? Because some other object may be doing the trick. But this requires that you have a different object that will guarantee that something is F. And that's how we typically are going to block the validity of this inference in classical logic. There, as we saw, identity is tied to quantification, and we have all the resources to block these things. Right? Here's exactly the situation we don't have. We cannot block those inferences. Now, someone may say, but wait a minute. You can say that the collapse here only holds because quantifiers is being restricted to these non-individuals, right? And in the case of non-individuals, since they are indistinguishable, of course, if what holds from one will holds for other, and then you will get that collapse. That's expected, right? But there is in fact, no such collapse any more than there would be a collapse if we were restricting quantification when a context only there is one object, right? Of course, if there is only one object in your domain, if something is F, everything is, right? So the thought is, well, look, it's just because you would expect to be that collapse if you're just dealing with this kind of quantifier, with non-individuals. And moreover, you don't even need identity, right, to resist the alleged collapse of the quantifiers. Why? Well, here, A is F doesn't guarantee that everything's F, because some object may not be F, and that's enough to block the inference. Similarly, something is F doesn't guarantee that A is F, since A may not be F. No talk about identity, so we say, look, we don't really need identity to preserve to show why the inferences are invalid. Okay. Now, so I have a number of considerations here, right? I don't think that this is quite right. Right. So first, I think the analogy with the single object domain doesn't quite go through, right? Because the collapse will take place even if quantification is not restricted to non-individuals, but also includes individuals, which is the case, in Quasiset theory, right? We have quantification over the micro objects and the micro ones. Now, it's true that non-individuals do behave in a rather unusual way, right? Given their indistinguishability. So that's granted, right? Despite that, although non-individuals of the same kind, say electrons, are indistinguishable from one another, they are supposedly different from individuals of distinct kinds, say protons. Right? You want to say, yeah, electrons are different from protons. Right? They have different charges. But that means you're talking about these things as having identity conditions. And you need to do that. So one question is, how can you say even those things if these objects are not open to the kinds of things for which identity applies? Now, to assert that electrons are different from protons requires that both such non-individuals have identity conditions. Right? But that's what's exactly being ruled out. Note that the claim is that electrons and protons are different, not just that their equivalence classes are. Right? Because you may say, look, of course, all the electrons are lumped together in the class of being indistinguishable from other electrons. All the protons are lumped together in their indistinguishability class. And of course, these are different equivalence classes, right? But the claim is not that their kinds are different, right? You're talking about electrons. An electron is different from a proton, right? And for that, it looks as though you need to assume the identity of these things. So it looks that even non-individuals will need to have some identity conditions, right? Even to express certain features about them. Okay, but this, of course, will be incoherent in the context of the claim that the identity doesn't apply to these things. All right. Moreover, I think identity is indeed required to resist the quantifier's collapse. suppose, again, that the domain of quantification is not restricted to known individuals, so includes both individuals and known individuals. To resist a collapse, it was argued that A is F doesn't guarantee that everything is F. For some object, B may not be F, right? That was the argument, said, oh, we don't need identity in order to resist that kind of collapse, right? But I think for the argument, this argument to go through, B has to be different from A. Otherwise, you end up with a contradiction, right? Then A is F and A is not F, right? So the only way to prevent that from happening, you have to say that the object B here is different from A, right? The object that invalidates that everything is F needs to be some other object, right? Other than the object that is F already, right? So, and for that you need identity of these things. So again, this requires the known individual A to have identity conditions, since it's different from B, as opposed to the characterization of known individual states. Similarly, to block the collapse of the quantifiers, it was on the other side, it was said, look, if something is F, that doesn't guarantee that A is F, since A may not be F, right? No identity is invoked here. Well, suppose then it's possible that A is not F, right? So that this response will go through. Now, if A were F, the inference would not be blocked, since in this case, both premises, something is F and A is F, would be satisfied. So to block the inference and avoid the collapse, the object that guarantees that something is F needs to be different from the object that it's not F. But once again, identity will be required for that as well, right? So even here, so the idea is, if you unpack the inference on the top, the inference ultimately would require the identity, right? It will require that some object different from the one that it's not F is in place. Okay, so we're back to identity in that context as well. So, to conclude, right? For the reasons we discussed, I think quantification is very closely tied to identity, right? So in the domain of quantification requires identity in the classical set theory due to the extensionality argument, axiom. Second, the domain of quantification requires identity in non-classical set theories, such as in Quasiset theory, since the very formulation of the axioms of Quasiset theory invoked variables that need to play the same semantic role. So even there, the notion of identity is assumed. Thirdly, the domain of quantification requires identity in order to specify the range of quantification without set theory, so that distinct objects in the domain are covered. So make sure that you cover all of them, right? So not the same again and again. And finally, quantification requires identity of the objects that are quantified over. Otherwise, the existential and universal quantifiers would end up collapsing into one another, right? So those are, of course, there are other considerations that can be given, but those are some that would support the conclusion that identity does, quantification does require the identity of the objects. So we started in a somewhat sort of Quinian mode with a quotation from the book review of Geach's, and we end in a somewhat Quinian mode as well, right? With the claim that no quantification without identity. Thank you very much.